Alrighty, welcome to DataLab9. Today we're going to talk about networks. Really, this is just building on top of everything we know already about multi-level models and random effects. But I think it's interesting stuff. And so I'm going to start with just a motivating example based on emotions that will set the scene as to why people are starting to look at networks. So our emotions are functional. They motivate and organize us to respond to important stimuli and situations. Even sadness and other emotions that don't feel great are useful. So if you're sad, it usually means that there's a discrepancy between where you are and where you want to be. And that sadness can motivate you to rectify that discrepancy. But even though they're useful and functional, we're not slaves to our emotions. Our emotions can and often should be modulated. And this often takes the form of changing the duration of our emotional experiences. So in healthy emotion functioning, our emotions persist until our goals are achieved, but they rise and fall when appropriate. So if there are changes in our environment or even to our goals themselves. In contrast to this kind of rising and falling of emotions in healthy functioning, in depression and in other forms of psychopathology, we see emotion rigidity. So this is a counterpart to this flexibility. And this comes across as a contextually inappropriate persistence in emotions across time. And so we actually looked at this last week in our inertia term. And the way we operationalize this persistence is by collecting lots of data on the same person. So just like we have with the experience sampling, and typically it happens as people are going about their daily lives, so the data have high ecological validity. When you have an emotional time series for one person and for a second person, so imagine that these are two people who have reported on some emotion over time, you can operationalize this contextually inappropriate persistence in emotion by capturing something about the dynamics of these time series. So this person up here does not have a very predictable time series. And the idea here is that it's flexible. It's a system that's responding to external events and being flexible. And so one way to think about this is that if you were to take an emotion at any particular time point and try to predict what's going to come next, you would have a pretty hard time. It's not a very predictable system. In contrast, in depression, you would have something that looks more like this, where there's a wider range in emotional experience. And so that could be captured with the intra-individual standard deviation that we've previously looked at. But there's also a predictability in it. So if this was sadness, if you're sad right now, it'd be pretty easy to predict where you would be later. You'd still be at the same level of sadness. Yeah, and so that's what we did with inertia. And it kind of gets at this idea that emotions change across time and to a different extent across different people. And this inertia term would be captured if we were to draw it in this type of diagram I have here as this autoregressive arrow. So it's the arrow pointing at itself. So my happiness at the current time point predicts my happiness at the next time point. Same with anger, same with anxiety, same with depression. But as well as changing across time, our emotions change across states. And they influence one another. And we can expand this diagram and capture this idea of like crosstalk between emotions by adding arrows, not just pointing at the emotions themselves, but pointing at other emotions. So for example, if I'm angry right now, then that means something for my happiness at the next time point. If I'm happy right now, that means something for my anger at the next time point. And this is common. We find this in the literature a lot, where it's not uncommon to have like secondary responses to your emotions. So for example, you might become anxious after having an angry outburst, and we could codify that in this diagram by using that kind of arrow. So here, there are all possible arrows that could exist are in the diagram, but you'll notice that some are darker than others, indicating a stronger temporal association. This becomes clearer when we look at two different individuals. So this person on the left doesn't have as strong predictive associations between emotions across time as a person on the right, who has much darker and thicker lines. And these between-person differences in the predictability of emotions have implications for psychopathology. So the theory is that an emotion network with strong temporal connections would encourage the spread of emotions to other emotions across time, such that you end up in a situation where emotions are responding to themselves rather than rising and falling flexibly as conditions demand. So that's the theory, and the way we've empirically examined this in the past has been to use daily diary surveys. So these are data from Greg Fosco at Penn State. I worked on this when I was in grad school. And the kind of key thing here is that you have emotions measured every day for 21 days. And so this is what that looks like. These plots should be similar from our DataLab class on visualizing these type of data. They reported on their anger, depression, happiness, anxiety from low to high every day for 21 days. And these plots are always kind of messy and it's hard to take much away from them. But the idea is that there's lots of fluctuations in depressed mood from day to day, and there are a lot of between-person differences in these fluctuations. So we want to take these time series of these 4 different emotions for our 151 adolescents, and we want to make networks out of them. To do that, we go to our trusted multi-level model, and we build our network piecemeal. So we start with 1 emotion at a time. In this illustration, we are starting with anxiety. So anxiety for person I at the current time point, so time t. And we were predicting anxiety at the current time point with all the other emotions, including itself, at the previous time point. And so here you have all the other emotions at the previous time point indicated by t-1. And so these arrows are all lagged 1 temporal associations. So if I'm happy right now, what does that mean for my anxiety at the next time point? We can allow between-person differences in these edges to emerge by estimating random effects. So just like we did in last week's DataLab. And then we repeat this process with depression as the outcome, happiness as the outcome, anger as the outcome, and we end up with all of the 16 slopes we need to create a network for each person in our sample. And so this GIF is just cycling through each person's emotion network, going from the emotions that have the kind of least the weakest temporal associations to the strongest temporal associations. And so one thing that you can do is just take the sum of the absolute value of these slopes to get at this idea of networks that are more predictive than other networks. And again, the idea is that denser networks are self-predictive, responding to themselves rather than flexibly responding to changing situations. And so the participants who have these stronger temporal networks should have a greater psychopathology. And that's what we find when we take this emotion network density score. We find that it predicts greater number of depressive symptoms. When we break our sample down into a depressed and non-depressed group based on clinical cutoffs, we find that the depressed group has greater emotion network density. Cool. So that's kind of the theory. That's why it could be kind of an interesting thing to do. And people do it outside of emotions as well. So it's not specific to emotions, but I think it is a natural place to start. Okay, so let's go ahead and do that. Let's start building some emotion networks. So we're going to read in the EMA data. We're going to focus on sadness, anger, anxiety, and happiness. And you should feel free to switch these out with things that you care about. It doesn't matter if they're emotions. And we're going to load the MLVAR multi-level vector autoregressive package. So before this package, you would kind of have to do everything manually. You would, just like in the previous DataLab where you created a multi-level model and then you took out the random effect, you would run multiple multi-level models and then take out all the random effects and then combine them. This package by Sasha Eskamp makes life way easier. And some useful articles to check out are here, as well as the Aura package documentation is very useful. So it's useful not just because it runs the different models for you and kind of collects all the parameters. It also has other things that it does that are pretty useful. So one, you'll remember from last week, we have blank rows to stop the evening report predicting the morning report. And that's why we have the blank row in here. MLVAR will automatically account for this. And so it won't predict the morning with the evening. So we're going to remove this so that we don't get confused later on. So now you can just see I remove the blank row. And we're going to run this function on our data with our 4 variables, specifying our ID variable. We want a lag of 1. And this is how it kind of avoids the issue of predicting the morning with the evening. It asks you for your day var, so the variable that indicates what day of the study it is. And so for us, it's day. And the beep var, so this is the momentary report. So in our data, we have 6 momentary reports, and we have a variable that indicates which one of the 6 each day it is. So it's daily response, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And so it's just a way to make sure that the order is right. So when we run this, it doesn't take a whole lot of time. I mean, like, it's dependent on how many variables you have and how many people you have, but it in all instances, it tends to be pretty quick. And one thing I just wanted to highlight is that the warning errors it gives are pretty useful. So in this case, it's telling us that we have 5 subjects with fewer than 20 measurements. Not super recommended to run analyses when you have this few measurements. So if we were, going on to publish this or whatever, we might seriously consider removing these people, or at least checking if the results hold when these people are removed. Then we can summarize the model, and I've just pasted it here earlier so we can look at this. Lots of output here, which we'll go through in more detail below. But the kind of main thing I want you to notice is that you get 3 different types of effects out. You get temporal effects, which tell you about how my sadness right now is associated with my sadness at the next time point. And it's kind of nicely organized into from to. So if you want to think about this as the arrow going from sadness to sadness or anger, anxiety, happiness, you have the estimate of this as well as a p-value. Contemporaneous effects. So this is contemporaneous, meaning at the current time point. So how is anger associated with sadness at the current time point? And you'll notice that there's only there's no directionality here. You don't have anger to sadness, sadness to anger. And that's because when you're at the current time point, you don't have the temporal association to know what came first. But it's still very useful to know how things are fluctuating with one another at the current time point. And then between subject effects, you can kind of think about this as the between person variable that we put in our multi-level models when we do the splitting. So it's basically saying, are people who are high in anger generally across the observation period also high in sadness across the observation period? And again, you don't have arrows because this is between person associations that don't make use of temporal precedence to try and get at the direction of effects. You'll notice that also we use the raw data. We didn't do any splitting of within and between person stuff. And that's because MLVAR does this for us, which again is great. There are different options of how you do the splitting. And so if you check out the package codebook, it will walk you through different choices that you can make here. The table is great, but it's not the easiest thing to interpret. And so there's some nice plotting capabilities with this package. And so we're going to plot the temporal network. And so this temporal network tells us about the within person temporal associations. And we're at the lag 1. And so what this is telling us is that if you're feeling sad right now, that sadness is going to persist into the next time point. So that's a green. Green indicates positive associations. If I'm anxious right now, I'm likely to be anxious at the next time point. And this is just like the inertia term that we looked at last week. But now, in addition to these self loops or autoregressive terms, we also have this crosstalk between emotions in the middle here. So if I'm angry right now, I'm more likely to be sad at the next time point. If I'm sad right now, I'm more likely to be angry at the next time point. For red, it's similar interpretation, just the opposite direction. So if I'm happy right now, I'm less likely to be sad at the next time point. If I'm sad right now, I'm less likely to be happy at the next time point. And so notice like these bidirectional associations which are intuitive and important, that aren't as easily kind of thought about or captured when we're kind of used to our typical dependent variable, independent variable, multi-level model scenario. And so this is kind of one reason I like this network approach, is that it kind of captures this complex interplay between emotions across time and other things, not just emotions. So that's the temporal network, the lag1 associations. We can look at the contemporaneous associations. So these are, if I'm angry at the current time point, I'm likely to be sad, I'm likely to be anxious, I'm less likely to be happy. And so the red and the green arrows, or lines in this case, are interpreted in a similar way to how they are interpreted in the temporal network. But the difference here is that you don't have the directionality, because it's not like you're talking about sadness at the previous time point associated with happiness at the current time point. These are all current time point associations. And then the final thing is between person associations. So this is can be interpreted like people who are high on anger on average, so across all of the 21 days, also tend to be high on sadness. People who are high on sadness tend to be low on happiness. Cool. So that's the network stuff. Here, the networks and the output are focused on the entire sample. So this is like for the prototypical person in the sample, what do these associations look like? You can get at individual networks by taking out the random effects, like we saw in the last DataLab. But instead of doing that, I'm going to go a lot more into person-specific networks in the next DataLab. So yeah, cool. So if you all want to swap out these variables for ones that you've been working with or ones that you were curious about, that's the homework for this week.